Okay, so to understand this exact value table, if you don't already, it's important to understand where it comes from and how to be able to reproduce it on your own. And the key degrees here are 0, which will just be assumed, 30 degrees, 45 degrees, and 60 degrees. And it also helps for you to know your unit circle for, imagine if you had a circle that was drawn perfectly with a 1 radius distance. That's why it's called the unit circle, 1 unit, called the radius 1. So imagine if you had radius 1. Well, it's clear if the radius was 1 this way, it would reach this spot on the x coordinate, and we'd have x 1 comma 0. And it's clear if we went all the way up here, we'd have one spot on here on the y coordinate, and it would be 0 comma 1, and so on around the circle. So the unit circle is important to keep in mind and to know, and to where it falls at these basic points to start. Okay, and this last one is 0 comma minus 1. And you'll also discover that the x, y coordinates of this unit circle, and I won't get into this yet, but the x coordinates and the y coordinates happen to correspond exactly with cosecant of an angle and cosine of an angle and sine of an angle, which means that x will be equal to the cosine and y value will be equal to the sine value for a 1 radius unit circle. And we'll get into that more in a little bit. Your first path towards this is understanding SOHCAHTOA and working with how to come up with these exact values here. So we're going to go to another sheet. And I might have to delete this table, but it doesn't matter. Let us draw a triangle. And let us make all the values on this triangle the same. Now, I'm going to start with a unit of 1. But overall, you should draw these with units of 2 in some cases, and you'll see why in a second as we go. But let's pretend we make all these sides 1. And I find this convenient for the unit circle itself. So it's a unilateral triangle. And it's clear in a unilateral triangle that the angles in the corner will be 60, 60, and 60. But now we're going to cut this triangle right down the middle. We're going to cut it right down the middle and form a 90-degree angle right at the bottom. Boom, on either side, doesn't matter. Now these triangles are identical. But what happens to this 60 angle that we cut up here? Well, obviously that's no longer 60, but each corner instead is 30. 30 here and 30 there. And obviously this side here is no longer 1, but either side is going to be half. Now, the reason they use 2, and maybe I should start with using units 2. So let's just start with units 2, and I'll work backwards to the unit circle. So let's just start with unit 2 instead. It'll make the math a little easier to understand. So I got 2 length here, and a 2 length here that got cut into half. So obviously this length over here is 1 from here to here, and this length over here is 1 from here to here. Now we're only going to use one of these triangles, so I'm going to just get rid of half of it. And we're going to bring back our rules of SOHCAHTOA. So if you don't know SOHCAHTOA, that's your first step. You've got to go back and learn that SO means the sine of any angle is equal to the opposite side, and only for a right angle triangle, over the hypotenuse. And cosine of any angle is equal to the adjacent side, only for a right angle triangle, over the hypotenuse. And tangent, TOA, tangent is equal to the opposite side over the adjacent side, sorry. And in case you're like, where'd I come up with that? This is just a rhyming feature. The O stands for the opposite, the S stands for sine. The S stands for sine, the O stands for opposite, the H stands for hypotenuse. Cosine, adjacent, hypotenuse. Tangent, opposite over adjacent. And it's just a memory aid. But that's your first step. If you don't understand that, that's the first thing you got to understand. Okay, let's focus on this angle right here. And by the way, the opposite is always determined on what angle you're talking about. So when I'm talking about 60 here, I'm talking the opposite is over here. The opposite over here. And the adjacent is over here. And so the adjacent is over here. And to do this, I need to know the height of this triangle. Well, thanks to Mr. Pythagoras, I know that the hypotenuse squared is equal to the one side, or the adjacent, plus the opposite squared, like that. And I also know that the hypotenuse is always opposite the right angle. So here's the right angle here, which means the hypotenuse is there. So that means I've got 2 squared is equal to the adjacent, which is just 1 squared, which is just 1 really, plus the unknown, the thing I want to know. So I end up with 4 is equal to 1 plus the opposite squared. If I use my algebra and I isolate my opposite squared, I get my opposite squared is equal to 3. My opposite squared is equal to 3. And to solve a square, I take the square root of both sides. So my opposite is equal to the square root of 3. So that's the length of my opposite. So I'm just going to put it up there, like that. And actually, I'll just use this one over here. So boom. Now I know my opposite has that length. Get rid of all that. Keep that in mind when solving. So that means my sine of 60 is equal to square root of 3 over the adjacent, or sorry, over the hypotenuse, which is 2. That's what SOHCAHTOA is. So it's going to be the opposite over the hypotenuse, which is this. And lo and behold, we have solved this one right over here. Sine of that angle. And as we continue, and we do, okay, let's do the cosine of this angle. It's the adjacent. What's the cosine? It's the adjacent over the hypotenuse. What's the adjacent? It's 1. What's the hypotenuse? 2. So we get the cosine of 60 is equal to the adjacent 1 over 2. And boom, we get this one right over here. And as we continue, the tangent of 60 is equal to the opposite, square root of 3, over 1, which is just square root of 3, right? So opposite over the adjacent. And that's where we get this one right here. Now you can easily figure out the cosecant, the secant, and the cotangent of these, because all you do is you flip the fractions upside down. That's all you do is you flip them upside down. What's this one? Square root of 3 over 1. What would the flip be? 1 over square root of 3. But we'll get to that. We've essentially just figured out this entire row right here. Quite easily, actually. And then as we do that, now we can focus on another angle. Up here, we can focus on angle 30, get rid of everything we've discovered. And we can discover that angle 30 has a different opposite. Its opposite is over there, and its adjacent is there. I also want you to notice that angle 30 shares the side and the adjacent and the hypotenuse as angle 60. So that can be very, very, very useful for remembering it. But we're going to go through SOHCAHTOA. So SOHCAHTOA says opposite of this 30 is this 1 over here. Opposite side. So that means the sine of 30 is equal to the opposite side 1 over the hypotenuse 2. Sine of 30 is equal to 1/2. Right there. Now I also want you to notice this relationship between this and this. And you might say, well, why does that relationship exist? Well, because they share the same triangle. It's just their opposites and their adjacents switch places depending on which angle we're talking with. That's why there's going to be this relationship between them. And that's why there's this relationship between them. And you're going to find this common relationship with sine and cosine over and over again. And it's clear why later. But as we continue, sine of 30 is equal to this. Cosine of 30 is equal to the adjacent, which is now this is no longer the adjacent to anything. Opposite anything, it's the adjacent. So we get the square root of 3 over the opposite, over the hypotenuse, which is 2. So over 2. And we discover we get this one right there. And continuing on, the tangent of 30 is equal to the opposite over the adjacent, which is the square root of 3. So 1 over the square root of 3. And that's what we get right here. So boom, we now have figured out this row using 2 simple triangles. And this triangle is very useful, and it's the one you should start with because you can figure out 60 and 30 at the same time. And you might say to yourself, why will this work for the unit circle when maybe I have to use one? And I'm going to get to that when we get to the unit circle, but I want to move on to my 45-degree triangle first. Let's look at a 45-degree triangle. How do you create a 45-degree triangle? Well, you take a right-angled triangle and you make both these corners 45. And by making both these corners 45, you are making the sides the same. So this side is going to be the same as that side. It's the rule of triangles. You cannot construct a triangle with two 45-degree angles without making the sides the same length. And as a result, this ends up being 90 degrees. So that's how we start. And just like the last one, we're going to make this 2, and this we're going to make this 2, and you can even get rid of, you can even get away with making it. Actually, let's just make them 1 and 1, even though it doesn't work as well later on, and we'll get to it. But if I make it 1 and 1, the only thing I'm missing now is the hypotenuse. Well, the hypotenuse is equal to this squared. The hypotenuse squared is equal to that squared plus this squared, a squared plus b squared, which is equal to 1 plus 1, which is 2. And then when I square root this, I discover my hypotenuse is the square root of 2, which is great. So I'm just going to steal this from here. Just going to get rid of all this. Boom. That's my hypotenuse right there. And then I bring up my old SOHCAHTOA. Now, it doesn't matter which angle I use because they're both 45, so they're both going to have the same opposites and the same adjacents. So I'll just focus on this one down here. And I'll notice, okay, well, sine of 45 is the opposite, which is 1, over the hypotenuse, which is the square root of 2. Boom. And sure enough, I see it right over here. And then when I take my cosine, I discover the same thing. It's the adjacent over the hypotenuse, and my cosine of 45 ends up being the exact same thing. And this is the only time the cosine of an angle and a sine of the angle will be the exact same thing. And there's this dynamic relationship between sine and 45, sine and cosine, as it relates to sharing a 90-degree angle. So I'm going to discover that, sure enough, look at that. They're the same. And then finally, when I go back to my triangle and say tangent is equal to opposite over adjacent, that's 1 over 1. 1 over 1, which is just 1. And boom, I filled out all this middle section of the table. And you might say, how do you figure out this stuff? Well, you use those coordinates and actually proving that the sine of 0 degrees and the cosine of 0 degrees are 0 and 1 is actually difficult. Because you can only get close to 0 degrees. You have to use a squeeze theorem. And even 90 degrees is kind of difficult because at 90 degrees there's no longer any horizontal distance. It's all vertical. And at 0 degrees there's no vertical distance. It's all horizontal. But let's just trust that those are the correct amounts. But really we only care about the exact values for 45 for these middle values. So we'll just skip this for now. And we only care about these. And then you say, okay, well, what about other angles? Well, it turns out you can indeed figure out the cosecant, which is just the same as 1 over sine, just by taking this value for 30 degrees and flipping it. What's the flip of this fraction if they switch spots? It's 2. So we get cosecant of 30 degrees is 2. And the secant, which is 1 over cos, means I'll just flip the fraction for this as well. Flip it. It's 2 over the square root of 3. And then what about cotangent? Well, cotangent is 1 over tan. So I'll just flip this. What's 1 over square root of 3? It's square root of 3 over 1, which is square root of 3. What about flipping this one? What is the cosecant of 45? Well, it's square root of 2 over 1, which is square root of 2. What about flipping this one? It's square root of 2 over 1, which is square root of 2. It means the secant of 45 is square root of 2. The cosecant of 45 is square root of 2. What about flipping this one? Yeah, okay, we'll flip 1 over 1. It still becomes 1. So the cotangent of 45 is the same as the tangent. The only time you get into some stickiness is for 90 degrees and 0 degrees. And we'll get to that in a little bit later. Let's look at this one. What about the cosecant 1 over sine of 60 degrees? Well, we flip that. It's 2 over the square root of 3. Secant, it's flipping of that. 2 over 1, or just 2. Cotangent, it's the flipping of that. Well, that's essentially over 1. So you get 1 over the square root of 3. And boom, by knowing your basic triangles, you will now know secant and cosecant. Very, very handy. Learn your 3 triangles. Once you learn them, you can reconstruct this exact table. And then we also can fill out all of these if we need to. Now, what about here and here? If I want to figure out the cosecant, which is 1 over the value of sine, 1 over sine, I got 1 over 0. So the cosecant of 0 degrees is not valid because you cannot divide by 0. So when we get further into this, we'll discover there's some values for cosecant and secant and tangent that can't exist. Well, I can flip 1 upside down, no problem. That's going to be 1. But when I flip this upside down, I get 1 over 0. It cannot exist. And we discover that also for the 90 degrees, while the flip of cosecant, and I should put a 1 up here, the flip of sine, rather, to produce cosecant is fine. When I do this one, I get not valid. And A. And when I do the last one, which already isn't defined, I get, I think actually, should look into that. It's opposite sine over cosine might be 0. Let's pull up the, do a 90. Yeah, I think that's actually 0. So 90, and we'll go to trig, and we'll go to cotangent. Oh, no, we get invalid input. My bad. So we get this invalid input probably because cotangent was invalid to begin with. And when we get into cotangent, why cotangent is invalid, we discover another formula later on that sine over cosine is equal to the tangent value. And we discover since these is a sine, 1 divided by 0, cosine, we get an invalid answer. So if I do 90 and hit tangent, invalid input. If I hit 90 and hit cotangent, I get invalid input. So that's an NA for here. And the only one of these values here that is NA, because it's the only time we get a 1 divided by 0. You're also later on going to learn a little interesting thing, which is the sine of 10 degrees is the same as the cosine of 90 minus 10, which is equal to the cosine of 80. And there's going to be these intricate relationships between 90 degrees, cosine, and sine. So you're going to get all this other information, but right now we're just working on the exact values and how to figure them out. How does that relate to the unit circle? Yeah, well, for the unit circle, I'd have to go back to those triangles. And instead of using lengths of 2, I'd have to go back and use lengths of 1. So this would be 1 here, and this would be a half here, and this would create this interesting situation, which would still be, let's see, 1 plus 1 minus a quarter square root of 3 over 2, I think it would be. And you get this weird triangle over again. But what it allows me to do is see how to fit this triangle perfectly into the unit circle. So if I have a unit circle here, and I have a circle with a radius 1, right? And it's clear this hypotenuse here has 1. It means I can fit this 40, actually that's a 30-degree triangle. Was it 30? No, it's a 60-degree triangle perfectly. I'll draw it in red. Right here, because the hypotenuse is 1, so it fits within my unit circle, which has a radius of 1. And I discover this length over here is a half, and this height over here is the square root of 3 over 4, which is square root of 3 over 2. And if you know anything, well, you know you've traveled x out and y up. So that means this xy coordinate is going to be a half and square root of 3 over 2. And then we remember that this triangle is 60. And when we look over at the sine of 60 right here, we discover, wait a minute, the sine of 60 is also square root of 3 over 2. And the cosine of 60 is 1/2. And as we go around and fit this triangle, because we can do this over and over again, we can do it with 30 degrees and we can do it with the 45, we discover this connection between the xy coordinates and the cosine and the sine values. And we soon discover that the xy coordinates in the unit circle are the same as the cosine values and the sine values of the angle that they would form right over here. But the nice thing about the unit circle is once you figure out how to fit a right angle triangle, because we can fit every right angle triangle in here as long as we keep the hypotenuse 1, that once you figure all that out, the exact same triangles exist over here. For instance, if I draw a 1 hypotenuse here that's 30 degrees, I discover that the length over here is the same as square root 3 over 2. Yeah, you got to draw a straight line down, so the length to here to there. And I discover the height over here is a half. And I discover, oh, coordinates are square root of 3 over 2, comma half, which happens to coincide perfectly with cosine and sine value. So this is cosine, comma, sine. But over here on this side, I can also fit in the exact same triangle with the same length and the same height, so it's going to have the same coordinate. But what happened here is I went left. I still go up on the y value, but I went left on the x value, which means the x values are actually negative. And the y values are still positive. But I still have the same number values. I still have a length here that's square root of 3 over 2. And a height here that's a half. Just this one is negative right here. This one's negative. And that's why when we get into the quadrants, we get the cast system. Because sine over here, which is, we know the hypotenuse is still 1, and this is 30 degrees, and we know sine is opposite, which is positive a half, over positive 1. So that's why sine is positive in this area. But because we're working with a negative adjacent now, and cosine of 30 is the adjacent over the hypotenuse, we discover, oh, well, the cosine is negative in here. And because tangent is opposite over adjacent and the adjacent's still negative, we discover, oh, tangent's also negative. And that's why the cast rule comes about, because as I place that same 30-degree triangle into my unit circle and go all around, I get all these values as x and y. But the x's in this quadrant, well, what are the x's in this quadrant? Positive. What are the y's? Positive. What are the y's in this quadrant? Positive, but the x's are negative. What are the x's in this quadrant? Negative, and the y's are negative. That's why tangent here is positive in this quadrant, but cosine and sine are negative. And then finally over here, the x's are positive and the y's are negative, which is why cosine, which works on the adjacents, is positive in this quadrant. And that's how the cast system came about. That's how the xy coordinates for cosine came about. And that's how we're able, once we figure out 90 degrees, we're able to figure out all the other quadrant angles. We're able to figure out 260 degrees, because 260 degrees, it forms a 80-degree triangle over here. Therefore, it's the same as the 80-degree triangle over there. We just have to use the cast system to adjust positive or negative. So once you learn 0 to 90, you know the whole triangle. Once you know the whole, you know the whole circle. Once you know the whole circle, you know every circle. And every circle after, even if I go round and round and create 540 degrees, it's still based on the first circle. That's why we learn all this. And it all leads to something else.